Hello, everyone. My name is Zabrocki, and I'm delighted to see so many people here because it's 9:30 in the morning, and I guess it's not the best hour to start the talk and day today. It's too early. Anyway, but I'm so happy to see so many people here today. And I would try to take you to the journey together with me about software vulnerabilities and unsolved memory safety problem. There is a couple of questions which we need to answer today. However, this topic is so important because we try as an industry to solve this problem for more than a couple of decades, and we still didn't do it. So what's the catch? What are the trends? What people has been doing, entire industry has been doing for the last 3-4 decades? What are we going to do in the future? And where we are today on this timeline. However, am I even the right person to speak about such an important topic? Yes. So my name is Zabrocki. Among others, I use nickname PA3. Currently, I'm working as Director of Offensive Security at NVIDIA, which obviously means I'm leading various offensive security research efforts inside of the company. But I'm also serving as a Vice Chair of J Extension Group for RISC-V CPU ISA, which means I modify the CPU itself, and I'm author of the hardware extension like pointer masking, hardware control flow integrity, memory tagging, and some more things. And I also security architect for the GPU and next generation NVIDIA products. In the past, I used to work for Microsoft. I'm one of the authors of Windows ATP, especially for the kernel exploitation detection driver. I also designed and wrote the driver for Windows System Guard runtime attestation / monitor service. Also designed Win32 ISO-HEAP. I designed Windows Return Flow Guard, which I own patent for. And I also used to work on EMET and SORA, etc. I used to work in European Organization for Nuclear Research, known as CERN, HISPA Systems, known from VirusTotal, Wrocław Center of Networking Supercomputer, and a few more. And I'm kind of boring person because on my spare time, I also do security research, to surprise. And I do bug hunting. I found bugs among other in Hyper-V hypervisor, KVM hypervisor, vGPU, Linux kernel, FreeBSD, OpenSSH, implementation of the stack cookies in the GCC compiler, RISC-V ISA design per se. I also found the bug in the Intel reference code, Intel microcode, Apache, XPDF, and a few more, and I have CV numbers for those. I also like studying exploitation techniques and mitigation techniques, which actually we are going to speak about today. And some of the things which you should not do during design such kind of technology, what you should do and should not do, which is even more important. And this research was published in the Frag magazine. I also designed Linux kernel runtime guard, defended by OpenWall, RSE, which is reverse engineering framework. I also had the pleasure to be a speaker in the Black Hat US, DEF CON, Security B-Side, Open Source Tech, and of course Confidence, which is one of the best conferences which we have. And also I've been nominated to the Pony Award twice. So why we even care about software vulnerabilities? I think this is a fundamental problem which we as a security industry kind of know about. But why we care so much about that? And there's various reasons why. This is one of the examples that in 2003, we had the world's second most widespread blackout of the history, which affected more than 55 million people, which did not have electricity. And if you read about what's actually going on, that people didn't have energy for more than 8 hours, it was caused by the software bug in the alarm system and in the control room, which means that software vulnerabilities actually went beyond the IT industry. It affected the real life of the real people. Our flight V88, which was actually a mission by European Space Agency, which is equivalent of NASA in Europe. And they launched in the 1996 their new rocket called Ariane 5. And this Ariane 5 actually exploded 37 seconds after the launch, which burned $370 million at that time. But we had the chance to analyze that, and what actually happened, we realized that inside of the software, it was badly designed. We found the dead code, which never executed. We found that there is unintended logic for the Ariane 5 rockets because it was carried out from the Ariane 4 rockets, which should never be there at first place. We also had insufficient protection in the integer overflow, which was actually a root cause of the problem, because this integer overflow was caused exception, and this exception incorrectly was handled. And this incorrect handling of the exception actually results in the halting of the entire navigation system, and as a result, the rocket explodes. Again, software bug, and we have a real-world problem. This is another example where the modern company is starting to switch to the service. From the economical perspective, service model is a little bit better for some of the companies, which actually results that many companies ship the fully equipped product to the customer, but it's locked in the firmware, which is actually a software. So if you unlock some of the features in the software, you have many features which are worth thousands of the money. That's an example of the Tesla, which some hackers unlocked 15,000 worth features. Stuxnet. This is a little bit more closer to us. So actually, Stuxnet is the first malware which was classified as a cyber weapon. But again, it exploded. It was written by, we believe, the two secret units in the United States and Israel. And it was targeting the nuclear program of Iran to be able to shut it down. And actually, when you read about how it works, inside of the Stuxnet, we saw at least 4 0 days for the software vulnerabilities, and it actually affected the real-world nuclear power plants. But as we know, such kind of advanced software, it's not as easy to control. Even it was targeting very specific environment. It was actually spread to other countries as well, including US itself. So it first was uncovered in 2010, but we know it was developed at least since 2005. SQL Slammer. So in 2003, we had one of the most successful infections in the history, which actually slowed down the general internet traffic. Not the specific servers, but the whole internet. The reason why, because SQL Slammer were exploiting the buffer overflow, which is obviously software vulnerability in the Microsoft SQL Server, but at that time, routers were not very well written, and the payload for the SQL Slammer exploit were crashing them. And because tons of the internet routers were crashed, the entire general internet traffic actually were slowed down. Another successful malware like that was Conficker, which was exploiting CV 2008-4250, which was in the Windows as well. And it infected more than 190 countries in the world. And what is also interesting, that the Conficker was so successful that the author of this malware did not dare to use it because of the attention it drew, because it was so fastly spread that the author was scared of their success. Duku. I wanted a little bit to speak about Duku, because Duku is an interesting passive malware. It was not active. It also exploited multiple 0 days in Microsoft Windows, and it's related to the Stuxnet worm itself. It has been created by actually the same unit, which is 8200. The reason I mentioned about Duku, because I wanted to speak about Duku 2.0. Duku 2.0 is one of the most interesting stories which I learned. So actually, in 2015, it has infected computers in hotels and conference rooms in Austria and Switzerland. So the question is why? So actually, at that time, on those hotels, there was international negotiation between Iranian nuclear program. So that specific malware were passive and listened in the conference room what was actually being discussed. It was also created by the same unit, which is 8200. But Duku went a little bit beyond, because it infected also Kaspersky Lab, which was reverse engineering and analyzing the Duku itself, Duku 2.0. During analysis, they breached their internal network. So because the breach of the Kaspersky 2014 happened, the Israelis who were able to control this Duku infection notified the United States that the Russians also breached the same Kaspersky Lab and were using the Kaspersky to receive the data from their customers. Eternal Blue, it is exploit developed by NSA, and NSA at some point was hacked by the shadow broker in 2017, and they leaked some of their tools. 2017 is a pretty important date. I will tell you why. And immediately after the leak of such kind of powerful exploit, the WannaCry ransomware popped up, later the NotPetya popped up. As a result, it infected multiple computers in the airports. Airline servers were also infected, and they canceled actual flight of the people. People were stuck in the airport sometimes for days. Again, through the software vulnerabilities, people couldn't fly. And what is interesting that a year before, in 2016, there is a proof that the Chinese hacking group also had access to the same tool, but the official leak of the tool was in the 2017. So the question is how they had access to the tool. I don't know, but we can guess. So yes, software vulnerabilities are important, as we know, and moreover, they can be used as a weapon today, which nobody expected in the past. So to make things even worse, as you can see on the slide, the trends, it's a little bit concerning because we don't see any sign that the amount of the software vulnerabilities every year are dropping down. It's opposite, it's exponentially growing. So the problem is going to be worse and worse every year, which these slides obviously show that, exponential growth. And we cannot speak about the software vulnerabilities without speaking about the memory safety problem. So basic question, what is memory safety? So memory safety is actually a term used by security engineers to describe the state of being protected from the various bugs related to the memory access. And memory safety bugs, not every memory safety bugs, not every security bugs are memory safety bugs. And memory safety bugs includes any type of the overflow in the memory. Is it stack, heap, globals, whatever you can choose. It's type of the memory safety bugs. Out of bound read and write is a memory safety bugs. Invalid page fault, including null dereference. Use after group of the bugs. There is tons of those, like use after free, use after scope, use after return. All of those are memory safety bugs. Unutilized memory are memory safety bugs. Memory leaks, stack exhaustion, heap exhaustion, invalid free. This is memory safety. But as I mentioned, not every security bug are memory safety bugs. So integer overflow, arithmetic overflow, underflow, this is not memory safety bugs. Logical bugs, error handling, race condition are not memory safety bugs. Although there is a star on the race condition because race condition on the memory access is memory safety, yes? But what is important, the reason I differentiate that, even the non-memory safety bug, they often result in memory safety bug, even they are not in their core itself. So if you do have arithmetic overflow on the how much data to copy between one piece of memory to another, the overflow itself, integer overflow, is not memory safety, but it results in the memory safety. So why we even speak about memory safety? Why we care about the memory safety? Because at first, memory safety is the biggest attack surface for the attackers as of today. And I really mean that. The reason, there is a question why. So at first, memory unsafe programming language, like C or C++, are developed at the core, developed a core execution environment, like Windows ecosystem, Macintosh ecosystem, Linux ecosystem, has been developed in the memory unsafe language. And again, there is a second question, why? Why this language has been chosen to develop these ecosystems? Because at that time when they were designed, we already had memory safe languages. We could choose memory safe language, but memory unsafe language has been chosen to develop this execution environment. There was multiple reasons why. First of all, the computers at the time were not as powerful to handle memory safe language attributes. Second of all, memory unsafe language allows developers for fine-grained control of their memory address, where it executes from. And it's important because memory at that time was a very expensive resource. We cannot just use as memory as we want to because it was too expensive and we didn't have it too much. So this is one of the reasons why we choose memory unsafe language at the time, even we already had memory safe languages. And memory safety bugs are very well researched. There is actually professional exploiters who develop exploitation framework targeting specific software stack. While I was working in Microsoft, I analyzed one of the pwn-to-own exploit. It was huge binary, and during reverse engineering, I realized there is multiple functionalities who allows to bypass mitigation in the Windows kernel. And when I was digging in, I actually realized that even this feature exists, they are never executed. So why the hell this big binary has so many features to bypass mitigations? So actually, we realized this is not an exploit. This is a framework which has plugged in zero-day inside. So there is a framework developed that you actually plugged in exposed primitives from the exploit, and it does entire exploitation process for you automatically and bypass all of the mitigations. Moreover, many researchers focus on the automation of the memory safety bugs detection without even understanding how the software works. Because memory safety actually could be pretty easy to catch. If you do have access to the source code, you can instrument the compilation process, and you have various code coverage-driven fuzzers, and it gives you bugs for free just by running it. And it sounds like theory, but this is actually a real problem who affected multiple million-dollar companies, billion-dollar companies, which at some point they couldn't ignore this problem anymore. And I want to speak a little bit about the Microsoft case, because this is the biggest software house, which, as we know today. And they was dealing this problem from the decades. And in 2002, Bill Gates himself launched something called Microsoft Trustworthy Computing Initiative. And the reason why, because Microsoft has been under constant fire from their biggest customers, which they have. So government agencies, financial companies, big banks. They said their business are affected by the bugs which Windows carried out at that time. So they couldn't ignore it anymore, because the customer demanded to make some kind of changes in the security state, because it actually affected their customers. So as a result, they created TWC, which focused on the 4 pillars, which is security, privacy, reliability, and business integrity. As a result, they actually developed something called Security Development Lifecycle, known as SDLC. Again, we're speaking about 2002. At the time, almost none of the security companies has any process of the security development. And Microsoft took a step forward and proactively changed that the process, how they develop the software, must actually care about the security. Today, almost every company has some kind of SDLC process. It might be called differently, but we do have that. They set the example how to do that. They also created MSRC, which is Microsoft Security Response Centers. Again, it was many years ago, and some of you might remember this time or not, but it wasn't obvious that we should care about the security bugs at all. There was a huge debate in the industry saying, OK, why we care about security bugs differently than any other bugs? Why usability bugs are less important than security bugs? If the customer cannot have functionality which they paid for, they will not buy the product, so why should I prioritize security bugs over that? So this debate was on and off. Nobody actually make any decision, and Microsoft at the time said, no, we actually should care about security bugs differently. We will do it differently. We will create an actual organization who cares about security bugs because it's important. And they created MSRC. As of today, we know it was the right choice, yes, because everybody has such kind of organization to be able to deal with the security bugs. In the past, it wasn't obvious. And because of that, they also spent tons of the money to actually hire the security researchers, which was, again, a little bit controversial at the time, because security researcher wasn't very liked by the company, but Microsoft starting to hire them and pay a really good salaries. So it was breakthrough scenario from the big company perspective. And these researchers starting to do constant fuzzing, bug hunting, exploit research, develop mitigation. And 12 years later, in 2019, they decided, OK, let's analyze the 12 years of all of the security investment which we've done. We paid a lot of resources and a lot of money to be able to improve ecosystem. Let's analyze what actually happened. Did we solve that problem? And they end up here. What do we see here? So actually, in 2006, 70% of the bugs are memory safety issues. 12 years later, 70% of the bugs are memory safe issues. Does it mean that nothing changed in these 12 years? We spent so much resources, we hired so many smart people, and nothing changed? Of course, something changed, yes. And that's what changed. The type of the bugs changed. As you can see, in 2006, almost a quarter of the bugs, 25%, were Stack Overflows. Because they were pretty easy to exploit. But if you look in the 2015-14, those bugs almost doesn't exist. They're almost not reported. Does it mean the Stack Overflow disappeared? Of course not. They are there, but they are not interesting from the attacker's perspective, because they're very difficult to exploit because of the mitigation which we have. So people just move to other type of the bugs. And then, as you can see, 2014, we have spike of this gray area, which is used after 3 bugs. The reason why, because there were not any effective mitigation at the time to stop exploitability of those bugs. I had the pleasure to work at Microsoft at the time, and we were working on introducing new mitigation, which will be effective to kill exploitability of these bugs. And as you can see, it worked out. Those bugs almost doesn't exist and dropping in the edge of this graph. But as you can see here, there is grow of this yellow box, which is type confusion, which means actually attackers move to different type of the security box, which is type confusion. The reason why, because type confusion did not have any effective mitigation to stop the exploitability of those bugs. So that's the trend today. So that's the Microsoft case. What about Google? There's another big company who produces the software. So when they wanted to develop the Chrome, they said, we do not actually want to repeat the mistakes which Microsoft had. Because Microsoft had an ecosystem which had security issues, and they starting to add the security layer on the top and solve those problems. Google said, when we developed the Chrome, we changed the idea. We will design the software with the security in mind from the beginning. We know this is important. Moreover, we only allow high code quality to be able to be put in the production, which means only the senior engineers will be able to develop the code on the production or must review the code which will end up in the production to avoid the situation there will be some kind of dummy issues. And moreover, they said, OK, we are still humans, yes? So even the smart people can still make mistakes. So let's hunt for the bugs in-house. So we did constant fuzzing since 2015. And this is important because the Google Chrome started in 2015. So they do constant fuzzing without stop since the beginning of the project. Moreover, they use various types of the fuzzers, not only one, various platforms, various fuzzers, custom fuzzers. Moreover, they're starting to use the Google Cloud Platform for fuzzing, which means they have essentially unlimited computer power. And again, that's another step in the security industry because it's a big breakthrough. Because Google Cloud Platform are not cheap. Any cloud platform actually not cheap. So why would we spend so much money of infrastructure of the cloud platform for handling some kind of the bugs? And Google said, no, that's important. We will sacrifice the money over the security, and you can use the Google Cloud Platform internally to be able to hunt for the bugs. And on the top of that, they also said, OK, we also need dedicated Google Chrome security team just to focus on the security research there. And they did actually the same study, kind of the same study, which Microsoft did. And in 2020, they analyzed all of the security bugs since the beginning of the project with the high severity and critical severity, which is important bugs. And they end up in this graph. So what do we see here? 70% of all of the security bugs are memory safety bugs. Moreover, half of those bugs are used after free vulnerabilities. And Chromium security architecture has always been designed to assume such kind of bug exists. And the code is very heavily sandbox, and to stop taking over of the host from exploitability of those bugs. But if you read this analysis from the Chrome, from their blog post, there's a quote. But we are actually reaching the limits of the sandboxing and the site isolation. So they divide the architecture in so many small components and isolate themselves, each of them between themselves, and sandbox them. There is not much they can do more. They are split it so much, there is nothing much to split. So we're hitting the limits of the sandboxing technology. So what about the open source? Maybe they solve that problem differently. So there isn't many information about open source, but there is a large study on OSS performed by the Technical University in the Darmstadt in Germany, Continental AG and Intel Lab, which can be summarized as we find no clear evidence that the vulnerability rate of widely used software decreases over the time. Even in the popular and stable releases, the fixing of the bugs does not seem to reduce the newly identified vulnerabilities. Again, how is it even possible? If you do have stable release, people hunt for the bugs, we fix them bugs, at some point it's kind of mature enough. How it's possible we still be able to find the new bugs? Because some of the bugs, we thought it's not a security bugs 20 years ago. Today, we know they are security bugs. So it's evolution of the offensive techniques, evolution of the offensive exploitability techniques, evolution of how the industry moved. Something which we thought is not a bug, now it's actually a bug. Something which we thought is not exploitable, today it's exploitable. That's why we have that. So memory safety, are we actually doomed? Open source couldn't solve that problem, at least as of today. Billion-dollar companies spent tons of the money trying to fight it for the decades. Even they took completely different approach, one from each other, and we still ended up in the same place. Does it mean that we are doomed? There is not much we can do. 2 decades of fights, and we're still in the same place? So generally speaking, no, because industry is researching and moving into 2 main directions. First of all, we're trying to leverage the safe programming languages, which can be flexible enough to develop a low-level software without sacrificing the performance. Such kind of language could be Rust, but even stronger attributes from the security can be achieved by using formal methods. So you can have formally verified languages who can prove, mathematically prove, there is lack of the memory safety issues. And additionally, can prove many more stuff. Can prove there is no undefined behaviors, type confusions. And an example of such kind of language could be ADA core Spark or formally verified Rust. There is an extension to the Rust who brings the formally verified features on the top of those. And the second trend which we can see in the industry, it's actually to leverage and modify the hardware to enforce the strong security attributes or mitigation in the software. The reason why? Because over a couple of decades of research, we actually learned that pure software mitigation failed. There is always some ways that people starting to play cat and mouse games. We patch something, they found a different way to bypass it, they found something, they patch it, so on and so forth. 2-3 decades of research, and we still couldn't find any way to stop such kind of exploitability. So over the time, we learn as an industry to be able to create effective mitigation, we need to split this mitigation over entire stack. We need to put the context to the hardware so the hardware can protect the software, and they need to have hybrid approach to be able to solve those kind of problems, to be effective. So we need to modify the hardware. So the question, what can we modify in the hardware to make security attributes stronger? So first of all, one of such kind of example could be hardware-enforced control flow integrity, which also includes hardware-enforced shadow stack, not the software. And but this type of mitigation is a post-corruption mitigation, which could still be relatively effective, yes? Another example could be hardware memory tagging. Hardware memory tagging is a completely different idea how the mitigation works, because it's a pre-corruption mitigation, which means that hardware can detect and stop the bug before it actually happened. So there is no room for the playground and for the bypasses. And another one, the last one I wanted to bring up, it's a little bit different than everything what I said before. It's called Cherry. It's completely new ISA, completely new architecture, it stands from Capability Hardware Enforced Risk Instructions. What does it mean? It means they actually change the concept of computer architecture as we think of today. Memory is not anymore just flat memory. Memory is actually an object in this Cherry architecture. Because if it's an object, which means that object can have attributes. These attributes can be security attributes in the hardware. And these attributes can be inherited when we take a pointer to this attribute, to this object, yes? So it opens completely different idea how the Cherry works. So I wanted to focus, I don't think I have too much time, but I wanted to focus on some of those. First one, I wanted to focus not on the Rust, because there has been so many publications about how great it is and how good it is. So I wanted to focus on the formally verified languages, which is a little bit different and stronger than just purely memory-safe language. So to be able to be secure, as Yoda said, we must pass formal verification to memory-safe B. So example of such type of language is ADA core Spark. ADA core Spark is actually a subset of the ADA language, which additional set of the analyzing tools. And the strength is actually in these tools, which is not proof, not stack, not test, not emulator. That's what the pure juice of the language is. And it can statically prove that there is that specific dynamic checks cannot fail. They can prove there is absence of runtime error itself, and can also additionally give you formal verification method saying that it's mathematically proven that such kind of problem does not exist. And because of that, you can have memory-safe attributes like in Rust, and it also have, for example, very strong typing system, much stronger than Rust. And there is no, because of that, there is no arithmetic overflows, there is no underflows, there is no integer overflows. Actually, there is no general types. I mean, there is, but nobody uses them when you program in formally verified language. So if you want to access the 3 bits in the register, you create a type of these 3 bits. And the formal methods will prove you that this new type will never overflow. And it traditionally has been used in the very critical industries, such like avionics, railways, defense system, because we don't want like air carrier to crash because of the memory overflow, yes? And additionally, when you compile the code in Spark, they produce a safety certified binary. And you can still have bugs in Spark, because the strength is in the analysis tool, and you might never run them, yes? And additionally, those tools are orthogonal to themselves. So if you want to be fully protected, you must run all of them, not just a subset of those. And I prepared here the comparison between C, C++, and Spark. Again, I don't have as much time, but generally speaking, general memory safety corruption are not applicable for Spark. They are actually, on the formal method, if you do it right, you will be safe from there. There is no problem with the general pointer security, from simple reason. Spark does not have pointers. No pointers, no problem, yes? It's not actually true. I'm a little bit lying, because in 2019, Spark introduced concepts similar to the pointers using a concept similar to the Rust borrow checks. So it has some kind of type of the pointers. There is more information on this blog post. And arithmetic security, as I mentioned, there is no overflow. You can be safe there from the integer, arithmetic, overflows, underflows. If you misuse the language by mistakes, for example, you forget the default case statement, you do assignment instead of comparison, Spark will prove you that this is something wrong there. So you're safe from there as well. There is something which we now move to a little bit more funky. What about the parallel execution? You have multi-threaded application. How can you prove that? It's very difficult, so this has become a little bit more sketchy. However, Spark working on the Ravenscar extension who's supposed to address this problem. And so what is left there? So what's left is actually logical bugs. So if you badly design the software, the Spark will only prove that the implementation of your design is correct or not and give you mathematical proof of those. But it cannot understand if your design is correct or not, yes? Because it cannot. So this is where the bugs could be. Additionally, if you, for example, incorrectly use the hardware, if you program the DMA in not correct way, there is not much things you can do here. So this type of the bugs will be in the formally verified language as well. But as you can see, there is not many type of the bugs you can still hunt in such kind of languages. So in the recap, you can have bugs because you might not run the tool, so you must run the tool, and you must run all of them, not just subset of those tools. And most of the potential bugs are in the design or logical errors. Actually, it's not true, because there is one group of the bugs which can be introduced by the compiler itself. I actually found such type of the bugs when I was reading the code in the Spark. I see, oh, they actually do defensive programming, they do many hardening, and you can see this in the code, in the source code. But then when you take the compiled binary, you reverse engineer, and you see that compiler itself optimized out some of the security benefits, so the bug was in the binary but not in the code. So this is funky, but it exists. It's not only to Spark 10 language. So everything sounds compelling, yes? But benefits, do we actually see the benefits of the software written in Spark? So I don't want to spend too much on these slides, but as I mentioned, I'm leading NVIDIA offensive security research, and we had a chance to analyze such kind of tools. So the main goal of our work is to work as a third-party, independent, and unbiased security team. And I really mean that. We are not pressured by anyone, by any manager, by any security, by any goals. We just do the job as an independent researcher. So we've done multiple projects between 2020 and 2022, and 17 of those projects were very high impacted. So some of them were written in memory's unsafe language, and some of them were written in Spark. So we wanted to take a look what we actually see on the statistics, what we found there. So first thing first, how do we even compare them? How do we compare apple to apple, not apple to anything else? This is a different project, yes? How do we even analyze them? So we pull raw data from everything what we had, and we categorize those projects through the types of the software which they do. And then we also categorize between time frame, total bugs, and what the project actually goal was. And we're then starting to compare. So in the project 4, in memory unsafe language, which was operating system-like software, and we had the same, not the same, we had different operating system-like software written in Spark. We spent 3 weeks of analysis on the memory unsafe language project, and twice as much in Spark, so 6 weeks. As a result, we found 45 bugs in the memory unsafe language and only 10 bugs in Spark. And 52% was memory safety bugs in the memory unsafe language, and 0% of memory safety was in Spark. Second project was not developed by NVIDIA, but it was boot control software in memory unsafe language. And we also have boot control software developed in Spark for the different project. We spent the same amount of the time on both of those, and we saw that one has 5 bugs, another has 17 bugs. Memory unsafe language has 65% of the memory safety issues, Spark has 0. So in the memory unsafe language, it looks like we also follow the industry standards of having 70% of memory safety issues. And the last project is a hybrid project, let's say, in Spark, which is equivalent of 2 projects in the memory unsafe, which is root of trust software and resource management firmware. And we had the same project having 2 features in Spark. And we spent almost the same amount of the time of both of those. Again, in memory unsafe language, we found 40 bugs and 28 in Spark. And there is 7% of memory safety in Spark. The question is why? So actually, this is the interfaces which are starting to interact with the memory unsafe languages and memory unsafe libraries, because it's not provable by Spark, because it's not in Spark. So in conclusion, formally verified software can be free of memory safety. It also formally verified software has much, much higher quality of the code, because it enforces secure and strict coding practice, strong typing, correct initialization of data dependencies, coding violations, such of that. And it's actually, how to explain, you cannot just sit down and write code in Spark, like you can do in C++. In C++, you just write a function, call it, loop it in the entire software. You have it, yes? Ship it. In Spark, you cannot, because in Spark, you model the state machine. So if you want to introduce the new feature, you need to introduce the object, how this object interacts with other objects, how does it change the state of the machine. So it's much, much cleaner way to develop the software, which results in the higher quality, naturally, yes? But as you can imagine, developers might not like it, because it's giving them much harder time to develop any software, and takes also more time. And also, in generally speaking, when we spent 4 weeks of the review memory unsafe languages, we found between 40 to 50 amount of the bugs. And when we take about 6 weeks of the Spark code, we found between 5 to 10 bugs. So it's completely different scale. So second stuff which I wanted to focus on, I want to focus on the hardware memory tagging. How does it work? What does it do? What does it require? So to be able to have hardware memory tagging, as I mentioned, you need to actually modify the CPU ISA. You need to modify the hardware itself. So hardware memory tagging sometimes is referenced as MTE. MTE stands for Memory Tagging Extension for the ISA, which is evolution of the hardware ASIN. Hardware ASIN is actually a software memory tagging, which also needs to modify the hardware, but in the less heavy way. And hardware ASIN is evolution of ASIN, which is address sanitizer, which has nothing to do with the memory tagging. So the jump between ASIN and hardware ASIN is much heavier than between hardware ASIN and memory tagging. Even the name doesn't say so. So what we need to change in the hardware? We need to have an ability to tag/color the pointers and ignore it during the memory reference from the performance reasons. We also need to have new instruction to maintain the tags and the colors. /colors. We also need to instrument every load and store operation, which is relatively easy in the RISC architecture, but like x86, it's not as straightforward. So I'm not aware of any memory tagging work on that architectures, excluding hardware ASIN. And we also need actually 2 types of tags. We need to have every pointer needs to have a tag. We can, for example, need to sacrifice 4 bits in the register to encode the pointer. And we also need to have every allocation need to be aligned to the memory block. And this memory aligned block need to have separate tag when you allocate them. For example, we need to have 16 bytes of memory and to have separate 4-bit tag. So how do we allocate the memory? Every allocation needs to be aligned. We need to generate the random tag, and we need to tag with the same tag the pointer and the memory. And during the allocation, we just change the tag on the memory, but not on the pointer. I know it sounds a lot of words, so how does it really work? That's a pretty nice example. So for example, here, we can detect easily heap buffer overflow. So we want to allocate 20 bytes, and we need to align this memory allocation to the memory blocks of 16 bytes, so we need to have 2 16 bytes blocks. So when we allocate the memory, we need to also generate the tag, or /color, however you call it. So let's say we choose the color green. So we encode the color green on the top byte of the pointer. So that's the real address of the pointer, and we put on the top of the byte the color green, which encodes the tag. And then we color with the same tag the memory itself. Now, if you do out-of-bound access, like, for example, P32, we're starting to cross the boundary of our chunks of the memory-aligned block and starting to touch the memory block with a different color. Now the CPU will check what the tag is, what the color is. Oh, so actually green and blue are different, yes? So the CPU will raise exception. So the actually corruption will never happen, because when we want to do corruption, the corruption will be caught at the time of actually trying to do the out-of-bound access. We did not do the corruption yet, and the CPU will raise the exception, and that's why we will catch it before the corruption. It's the pre-corruption mitigation. What about heap use after free? Again, the same example. We do have pointer. We tag the pointer. We tag the blocks. We deallocate the memory. We delete the memory, so we need to retag the memory color, yes? So now green become, for example, pink. Now the new block is pink, but we never retag the pointer. So when we use the dangling pointer in the memory with the old tag, the green does not match the new tag in the memory. So CPU will not allow you to access the memory which was freed because the color doesn't match, and now we have catch the use after free bug. So that's all what I have. I'm not sure if you have questions, time for the questions. But if yes, I'm happy to answer anything.
Any questions to Adam? There's one hand over there. OK, on my way, on my way.